All right, so we are going to finish up this proof of, I don't remember what proposition it was, but essentially the existence of this proposition 4, the existence of the saddle path solution in the Ramsey Neoclassical Growth Model. How does this proof work? It's basically a process of elimination type proof, right? We have on our phase diagram all of these different trajectories for capital and consumption over time. All of those trajectories are consistent with equations 1 and 2 of our model. 1 being the intertemporal solvency condition or intratemporal solvency condition, and the other being the consumption Euler equation. However, each and every one of those different trajectories ends up violating one of our boundary conditions, except for one, and that is the saddle path solution. For all of the trajectories that enter into region B and move, let's see, northwest on our phase diagram, we showed that eventually the zero lower bound on the capital stock would be hit, at which point the consumption Euler equation would be violated, right? You have capital accelerating towards zero and consumption growing enormously. But then all of a sudden, when the capital stock hits zero, consumption drops to zero because you can't have any output without any capital stock. All of the paths, so we can rule out all of those paths, right? All of the paths that eventually enter region D also violate one of our boundary conditions, but it's our boundary condition at infinity, the so-called transversality condition, which I want to show today. The first thing we needed to do, however, if you recall from last week, was that we wanted to show that every path that entered region D, and I've restated some of it here, eventually lead to this point K bar 0, where K bar is the maximum sustainable value of capital in the problem if consumption is selected to be 0 forever, right? It's where the KT plus 1 locus intersects the K axis on the phase diagram. And we showed that every single point in region D eventually has to converge to that same point, that specific allocation K bar 0. Now, what I want to do today to finish up this proof is essentially show that this particular allocation violates the transversality condition. Therefore, we can rule it out as a possible optimal solution to the problem. Okay, easy enough? Well, what does the transversality condition say? It says that the limit as t goes to infinity of the discounted value of the marginal utility value of the state is equal to 0, right? So the marginal utility of consumption times the real interest rate times the capital stock, the product of that discounted goes to 0, where beta is 1 plus the population growth rate over 1 plus the discount rate. Okay. Any questions then about that? So that's just jogging our memory from the last class. Now you'll notice that for any path that enters region D, there's going to exist some time, some finite time, let's call it cap t, for which the capital stock is going to be greater than the golden rule level of capital, but less than this maximum sustainable level of capital. And that's going to be true for all t greater than or equal to cap t, right? Remember where the golden rule level of capital is. It's the level of capital that is positioned at the peak of the KT plus 1 locus. Eventually, there's going to be some time, cap t, such that the capital stock is bigger than the golden rule, but less than this maximum sustainable level of capital. And for all periods after that, capital is going to be approaching this K bar. So it's in this open interval here. Now, to be complete about this, let's first prove that the golden rule level of capital is indeed less than K bar. Let's make sure we've established that first. All right, well, what does the golden rule satisfy? The marginal product of capital evaluated at the golden rule was equal to delta plus n. The peak level of capital, consistent with zero consumption, satisfied the following equation. F of k bar is equal to delta plus n times k bar, right? These were the two conditions satisfied by the golden rule level of capital, as well as this maximum sustainable level of capital. Well, this implies that f prime of k star at the golden rule is equal to delta plus n, which should be equal to f of k bar divided by k bar. And hopefully you see here that this implies that k star gold has to be less than k bar because f is strictly concave. But I'll graph it over here just to show you. All right, here is the production function, f of k. What this condition says is let's find values of k star and k bar such that the slope of the production function is equal to the secant, I think is what it's called, right? Let's say k bar is over here. Then this distance is what? This is f of k bar. And so what is f of k bar divided by k bar? That is the slope of this line segment. I think that's called the secant, if I'm remembering right. At what point is this slope equal to the slope of the production function? Well, it looks to me like it's about right here. So if the slope of the production function is equal to the secant, it must be that the point at which you're evaluating the slope of the production function is less than this k bar, right? And that follows because f is strictly concave. The second derivative is negative, right? Does that make sense? Okay. All right. So for any t bigger than or equal to cap t, so remember we're out at a point in time here at which point the capital stock is bigger than the golden rule, then u prime of ct is equal to 1 plus rho over f prime of kt plus 1 minus delta times u prime of ct minus 1. This is just the consumption Euler equation. Scroll back one period, right? It says u prime of ct is 1 plus rho over 1 plus rt times u prime of ct minus 1. So we've taken the consumption Euler equation and just scrolled it back one period. Well, let me employ a trick here that we've used a few times in this section. What I want to do is I want to use this equation to solve for u prime of ct. So scroll this equation back one period and substitute the result into u prime of ct minus 1, and then do that repeatedly, right? So this would be what? 1 plus rho over f prime of kt plus 1 minus delta times, what's u prime of ct minus 1? Well, it's 1 plus rho over f prime of kt minus 1 plus 1 minus delta u prime of ct minus 2. Now, if we do this for many, many periods, and I want to substitute iteratively all the way back to period cap t. That's what I'm interested in doing. So I'm not going to go all the way back to date 0. I'm going to go back to period cap t. What is this thing going to look like? It's going to be a 1 plus rho raised to the number of periods between little t and cap t, right? Divided by f prime of kt plus 1 minus delta, f prime of kt minus 1 plus 1 minus delta, times all the way back to an f prime of k cap t plus 1 plus 1 minus delta, times u prime of c little t minus the distance, the difference between little t and big T. In other words, this is equal to c cap t. Right, if I just kind of keep scrolling this equation back and substituting in, eventually you're going to get that the marginal utility of consumption in little t, in time little t, is equal to this product based on the number of periods between cap t, which was in the past, and little t, which is today, times the marginal utility of consumption at date cap t. Okay, does everybody understand that so far? All right, now here's where we're gonna do some employ a little bit of a trick here. So since we know that KT is bigger than the golden rule for T bigger than or equal to cap T, then this implies that F prime of KT has to be less than F prime evaluated at the golden rule, right? If the capital stock at date T is bigger than the golden rule, and that means the slope of the production function is less than F prime evaluated at the golden rule. Now, what is F prime of K star gold equal to? That is equal to delta plus N, correct? So that means F prime of KT is less than delta plus N for all little t bigger than or equal to cap T. Well, what does that imply? I'm trying to do something here to the denominator of this expression. That implies that F prime of KT plus 1 minus delta has to be less than delta plus N plus 1 minus delta, right? If F prime of KT is less than delta plus N, then F prime of KT plus 1 minus delta is less than delta plus N plus 1 minus delta, which of course is just equal to 1 plus N. Again, for all T bigger than or equal to cap T. This is only true once the capital stock is larger than the golden rule. Okay, does everybody follow me so far? Yeah? All right, now, actually, so what do I want to do? Let me go back up here and rewrite this expression. So this was U prime of CT is equal to this big product over here. Well, let's do the following substitution. If I substitute 1 plus N for all of these F prime plus 1 minus delta terms, then we know that the terms in the denominator are going to be bigger when they're equal to 1 plus N. And if the terms in the denominator are bigger, that means the ratio is smaller, which means that U prime of CT then is bigger than 1 plus rho to the T minus cap T divided by, imagine putting in a 1 plus N for every one of these terms. Well, then how many of them are there? There's exactly T minus cap T of them. And since 1 plus N is bigger than each of these terms, the ratio is smaller, and so U prime of CT is bigger than that times U prime of C cap T for all T bigger than or equal to cap T. Does everybody follow that? So I'm exploiting the fact that capital is bigger than the golden rule so that the real return to capital, net depreciation, we know is less than 1 plus n. So if I take out the real returns and substitute in 1 plus n, I know that the marginal utility of consumption today has to be strictly bigger than that. All right, let's start combining terms here. This is a 1 plus rho over 1 plus n raised to the little t times the 1 plus rho over 1 plus n raised to the negative cap t times u prime of c cap t. Well, what's that equal to? That's equal to 1 plus rho over 1 plus n is the inverse of beta, is it not? So that's beta to the negative little t times beta to the cap t, right? Because beta is 1 plus n divided by 1 plus rho times u prime of c cap t, which implies then if I multiply both sides of the inequality by beta to the t, you get beta to the t u prime of ct has to be strictly larger than beta to the cap t u prime of c cap t. Oh boy, now that's going to help us. That's for all t bigger than cap t. So we know that once the capital stock exceeds the golden rule, then the present value of the marginal utility of consumption at date t is bigger than the present value of the marginal utility of consumption at date cap t. All right. Well, what else do we know? We know that KT is bigger than the golden rule, right? But we also know that KT is less than K bar. So this implies then that F prime of KT is going to be bigger than F prime of K bar. Now, how can I use this? How can I do something to this inequality that guarantees that the inequality is still going to hold? Well, let me multiply the left-hand side by KT. That has to be bigger than the right-hand side multiplied by K star gold, right? If I just multiply the left-hand side by KT and the right-hand side by K gold, sorry, if I multiply the left-hand side here by KT and the right-hand side by K gold, the inequality still holds, right? Because KT is bigger than K gold. Let me also multiply the left-hand side by F prime of KT plus 1 minus delta, and the right-hand side by F prime of K bar plus 1 minus delta. Now, why do I know that that will hold? Well, if KT is less than K bar, then F prime of KT is bigger than F prime of K bar. And so again, I'm multiplying the left-hand side by something that's bigger than the thing I'm multiplying on the right-hand side by, so the inequality is still going to hold. And this must hold for all time little t, including infinity. So the limit as t approaches infinity of beta to the t, u prime of ct, f prime of kt, plus 1 minus delta times kt has to be bigger than beta to the cap t, u prime of c cap t, f prime of k bar plus 1 minus delta times k star gold. And we know that the right-hand side is strictly bigger than 0. Beta is positive, U prime is positive, the real interest rate's positive, the golden rule is positive. So what we've shown here is that the limit expression, that is what our transversality condition needs to be equal to 0, is strictly greater than 0. So the transversality condition is violated for K bar 0. So this particular allocation that all paths in region D converge to will eventually simply violate the transversality condition. Now, do you guys remember what, if the transversality condition is positive, if this limit expression is positive, then this is going to imply that the limit as t goes to infinity of kt times the product from j is equal to 0 to little t minus 1 of 1 plus n over f prime of kj plus 1 minus delta is strictly bigger than 0. In other words, what's happening here? If we are on a path that eventually leads to point k bar in 0, then what is happening to our lifetime budget constraint? It's not binding, right? What is the way, how is it that we can interpret the no Ponzi game condition? When the no Ponzi game condition holds in strong form, that is, this thing is equal to 0, then we've already observed that the family's lifetime budget constraint will bind, so that the present value of consumption over the entire life is equal to initial assets plus the present value of lifetime labor earnings. If instead this limit expression is positive, then what that's saying is that there are resources that are being unused by the family, that lifetime earnings exceed the present value of lifetime consumption. And that should be obvious if this is the allocation we go to, because that is such where families are saving and accumulating the highest possible of assets in the economy. So the capital stock goes to its highest sustainable value, and we consume nothing in the long run. That's obviously going to leave resources on the table that the family could use for consumption. And so the lifetime budget constraint is not going to bind. The transversality condition is violated, and therefore that is not an equilibrium that the family would choose. That's not going to be optimal because it violates one of the key optimality conditions, that is the transversality condition. That means there is only one equilibrium trajectory in KT-CT space that simultaneously satisfies equations 1 and 2, the solvency condition and the Euler equation, as well as our boundary conditions at 0 and at infinity. That is the transversality condition, and it's the saddle path equilibrium that converges directly to the unique steady state, which we characterized analytically and graphically in the last class. Are you guys starting to understand this a little bit more intuitively now, why the transversality condition and this no Ponzi game condition are so important in this class of models? Without it, the economy does not necessarily converge to any type of unique equilibrium. What the no Ponzi condition is doing, what the transversality condition is saying, is that in present value, the representative family will exhaust its lifetime resources on consumption. That the lifetime budget constraint, not the period by period budget constraint, but the lifetime budget constraint will bind, meaning that the present value of current and future consumption should be exactly equal to the present value of current and future wages plus initial wealth. And what happens here is that the representative family takes some given amount of initial capital, and determines the optimal value of consumption in the initial period. It jumps up to the saddle path such that the subsequent path of consumption and capital will lead it directly to the unique steady state, and the lifetime budget constraint will bind. The consumption Euler equation and the period by period budget constraint is what characterizes the path of consumption from date 1 to infinity. What is it that determines the optimal initial period of consumption? It's the unique level of consumption such that the ensuing path of consumption over time will cause the lifetime budget constraint to bind. That's why it's so critical to impose this no Ponzi game condition on the model. It guarantees the existence and uniqueness of this saddle path solution, which is the right way we want to think about transition dynamics in a model that has both states and controls. In a model like the Solow model that just has a law of motion for capital characterized by a single equation, we can think about the stability of the system by just taking the derivative of the mapping from KT to KT plus 1 in a neighborhood around the steady state. The stability of a system that is governed by both states and controls, the capital stock and consumption, requires us to use this phase diagram tool and to derive the saddle path solution. Any questions about that?